Hey everybody, we're back again here with lesson 10.5. This lesson is entitled Base E and Natural Logarithms. And base E, that's an odd thing. Actually, E stands for Euler's number. I'll spell that for you in a minute here. But sometimes mathematicians, in fact a lot of times mathematicians are really curious people that are looking for patterns and things. And years ago, a couple of mathematicians were playing around with a particular formula, something like this. And they wondered what would happen if we used factorials on the denominator here and let this bottom one, or this last one here, approach infinity. As R approached infinity, what would happen? They just playing with these numbers. And they discovered that this sum here approaches a particular number. And that number they came to define as, that number happens to be about 2.71828. It's an irrational number. But it gets closer and closer to this number. It doesn't actually get there. But as it's approaching this number, it was an interesting, just kind of an interesting little idea. Well, they coined this number, Euler's number. Now, for years I always pronounced this Euler's number because it looks more like Euler's to me. But I guess it's pronounced Euler's number. I'll probably say it wrong a few times because I've been saying it that way for so long. These mathematicians, they discover these curious things. But then over the years they tended to learn that there were practical applications for this particular number. They called it E. It's an alphabet letter here. And the kinds of things they discovered were numerous. Let's take a look at some of them. Well, they discovered this number happened to have particular applications in several different areas of growth and decay. Things like population increases, radioactive decay, like in radioactive substances, nuclear radioactive substances, carbon dating. We use that to calculate the dates of things. But particularly in the area of finances, like compound interest and mortgages. These are the applications, the practical applications for using E. There's lots of other ones as well. One of them happens to be from calculus. E is used in a calculus situation. Calculus is all about acceleration, or part of calculus, about acceleration and momentary rates and so forth. But these are some of the applications, and we'll look at those a little more in the next episode here. So this is the approximate value of E, 2.71828. And you notice I put the dots at the end here. This is an irrational number. Let's take a look at where you can find this on the calculator. You won't really need to write this number much because the calculator has it available for you. Let's take a look at the calculator here. Alright, here's that number on the calculator. I put in E here, and I'll show you where that's at on the calculator. But notice the number that it's producing here, 2.718281828. It almost looks like this thing continues to repeat, but in fact it doesn't. That's just the digits that are visible on the calculator here. But where do you find E? Well, E is located in two spots on your calculator. If you look right above the division button here, in blue, the second function, you could put E in there, and that's what I did to get this particular calculation here. But E also appears at kind of a more important spot. It's down here just above this button called the ln. That's a natural log button. See right above it in blue, it's E to the x. And that key is used a lot. And so you could punch that button in as well. We use it probably more than the E button. So second, E to the x, and then you would be able to type in a number for E to the x. Let's just type in a number here. How about E to the third? That gives us a value of 20.85536 or so. Now, is that right? Well, let's take a look at this here. If E is approximately 2.7, that's somewhere between 2 and 3. If I raise 2 to the third power, I'd get 8, and if I raised 3 to the third power, I'd get 27. And look, the number that we got was 20.085. So 2.71828 is in between those, so I would expect that e to the third would be between 8 and 27, and in fact it is. So that button, e to the x, is a button that we will use on a regular basis. One other thing to make just a side note here is that because of the use of the letter e, we're going to try to avoid, if possible, using e as a variable. Right from now on, if you use the letter e for a variable, you might end up confusing people, and they might think, oh, are you talking about Euler's number, or are you talking about, e? So sometimes if you have a problem with, say, elephants or electric eels or something, you might want to use the letter e for your variable, but I would discourage you from doing that because people will get that confused for e. All right, let's move on. So what you may end up finding is you'll get problems that might look like this. E to the x equals, say, 5. And what this is asking is the same question we've been asking all along with exponentials, and that is, e to what power is going to give me 5? Well, in order to solve equations like this in the past, you had equations like 2 to the x equals 5. We would take the logarithm of both sides to solve this. Our whole goal is to get that to come down on the line using one of the properties of logs. Well, it's the same here. The base e and the base 2 and every other base, everything is done exactly the same, except for now, instead of putting a number there, we're going to put the letter e there, just like we would put the letter pi to talk about 3.14. We're going to put the letter e there to discuss that. So let's do a little quick review about using undo operations to solve. Now, just a little bit of review here. Algebra is all about using undo operations to get the variable alone. Well, here, to get x alone, we would subtract 3 from both sides, do the opposite or the inverse. To get x alone here, we divide by 3 on both sides. To get x alone here, we would do the undo operation of square rooting, which is squaring. And we end up with these, the square and the square root undo each other. And same thing over here, with the square and the square root would undo each other. And now x is now alone, and this is plus or minus 6. These are the undo operations we've been using. Well, so far in this chapter, we've discussed that in addition to that, to take something out of an exponential position, we have to use logarithms. So a base to the x power equals some result. We know that the inverse operation for that would be log base b of r equals x. So these two are undo operations. An exponential situation is undone with a logarithmic. These are undos of each other. And being able to reproduce this pattern is something we started a couple weeks ago. Let's take a look at a couple. Well, one final thing before we move on here is that we're going to be using a new logarithm notation. We could write it log base e of something, let's say 2, but because we're using this base called e, there's another notation which is called the natural log. Natural log. And the reason it's, I guess, called a natural log is because it occurs naturally in nature, just like pi occurred in nature to deal with circles. This occurs in nature. And they will use the notation ln to talk about the natural log of base e. Now, I'm going to continue to write this e here. All three of these mean the same thing. Log base e is equal to log ln, which is equal to the natural log base e. These are all the same. I tend to prefer this one out here because it reminds me that I'm working with natural logs, and it also reminds me that the base is e. So I'll be using this notation mostly. I may come back and do one of these others. Your book uses this one in the middle without the E there, but I think having that E available is fine. But you know, you could write it in any of these three manners and it would still be correct. All right, let's take a look at a couple simple problems. All right, let's take a look at this. By the way, you'll notice that I'm using a cursive L here. You'll see sometimes people will use a capital L. But if you use just a regular L like this, it looks funny. It looks like one L, and that just looks odd to people. So I wouldn't use this notation. Either use a cursive L or a capital L. Either one's fine. So all we're going to do is we're going to now use the natural log button. So if you look at your calculator here, the natural log button happens to be right down here, ln. ln's here. So if I punch in the natural log, now notice it's not showing the E there, and I type in 4, what it's asking is, what is the exponent on E that will give me 4? Well, the exponent on 2.7 that'll give me 4, it's got to be a little bit more than 1, and that's what we got here, about 1.3, 1.4. What is the exponent on E that will give me 4? So if I raised E to the 1.38629 or so, I would get 4. Let's just prove that. I'm going to use this E to the X key and just prove this. E to the X, and let's put in this exponent, 1.386294361. Put that in there, and my answer ought to be real close to 4. And it is, okay? It probably rounded it off a little bit. So once again, what it's asking is, what is the exponent on 4 that will give me, the exponent on E that will give me 4? And there's the exponent. So if I take E and raise it to that power, I should get 4. I'm a little surprised that it gave me an exact answer here, because this is probably a rounded number in my calculator that I just typed in, so I'm a little surprised. It must have rounded it off for us a little bit. Let's look at another one. All right, let's take a look at this one. Now this one seems a little odd. We're taking the natural log base E of E. Well, let's see what happens if we put that into the calculator. Natural log, its base E is not showing there, of E, so second E. Natural log base E of E, and you'll notice I get 1. Well, why is that? It's because, again, a log base and a base are inverse operations of each other, and they do one another. Now, why does that work? Well, let's take a look at the algebra and why that works. Let's set a letter here, N, and say, what would N have to be in this situation? Well, let's drag the result down. Throw the base to the other side. This base is coming over here. And apply the exponent. What would N have to be? Well, what you don't see right here is a 1. See, the natural log and the natural log base E and E undo each other, and they create 1. It creates 1, and this is an important concept for us to understand, is that these two undo one another. This is a serious thing, as we're going to use this to solve equations. Let's do a couple other problems. Now we have a problem that's an exponential problem, and in order to solve an exponential problem, I have to use its inverse, which is logs. To get x down off of that perch up there, come down on, I have to use logarithms to solve this. In this particular case, because this is a base E, I'm going to use the natural log, but I could use any base if I wanted to. But using the natural log is the easiest base to use here, and I'll show you why. So we're going to take the natural log of both sides, natural log base E of E to the X. Now I'm writing the E here, even though your book doesn't do that. Okay, this comes down here, there's the 5. I've taken the natural log base E of both sides. Well, if we roll that around to the front and multiply, remember, when the request is to power something, we find ourselves multiplying. I'm going to roll it around to the front and multiply it. This is the same principle we used in the past. Nothing's changed here. The bases only thing that's different, and it doesn't make any difference on the way we solve this. Now, what is that? Well, these two undo each other. I could divide both sides by this, but I'm really just dividing by 1. This is just 1. They just undo one another. And so the answer here is x equals the natural log base e of 5. And then we could use our calculator, punch that in. And here it is again. So I'm going to clear this. Natural log base e of 5. And I get 1.6094, rounding to 4 decimal places again. I probably should be putting an approximate symbol here. We know that all of these are approximations. So in other words, we're using the same principles we did in the past. You're taking the log of both sides. But if we use the natural log with the base of e, we're going to find a shortcut because this is going to go out. These are undo operations, and this is out because they undid each other. They undid one another. And that's key here. They became one. All right, I want to make this point one more time here. If I was to solve this and evaluate it and find out what it's equal to, well, I know that these two, the log base e and the base of e, undo each other. This should be equal to 4x plus 2. Let's prove that. And let's put a letter in here, say n. Okay? We're going to drag down the whole result. And the whole result is e to the 4x plus 2. Put the exponent to the other side. And apply put the base to the other side and apply the exponent. And as you can see, they have the same base, so the exponents must be equal here. So once again, the natural log base e and e undo each other. Just like the log base 5 of 5 is also equal to 1. So the property is still the same, that these are undo operations of one another. All right, let's look at a little harder problem. I want to underscore that these problems are done exactly the way they were before, with the solving both sides, doing the same thing to both sides. It's just that now our base is e. Remember, this is not a variable. All right, our only variable we have in this problem is x. E is not a variable. So if I want to get ex down and solve for it, I have to get it off its perch up here. And in order to do that, I'd have to take logs of both sides. But I don't want to do that yet because my goal is to work backwards through what's been done to x. So let's revisit how x was built, or how something was built onto x. So x was made negative, then it was made the exponent of e, then it was multiplied by 5, then 7 was subtracted. You notice we worked in the order of operations there. X was multiplied times a negative, it was made a power of e, then it was multiplied times 5, then 7 was subtracted. So what do we do first? Well, we work backwards. The last thing done, we're going to undo first. So let's add 7 to both sides. Bring down the leftovers here. Now the last thing done to x was multiplying by 5, so we're going to divide both sides by 5. You'll notice we're slowly getting x alone. Now, we're ready now to undo this and get it down onto the line. So we're going to take the log of both sides, and I could use any base if I wanted to, but it's easier if I just take the natural log base e of this. Both sides, natural log base e of 9/5. Okay? Just taking the natural log of both sides. And then now we're going to roll that around to the front because of the powers of powers rule. And I get this. Now I'm writing this out this time, but in reality I know that's going to go out. And we end up here with this. This is going to go out because a log base and a base undo each other. And we've got negative x equals the natural log base e of 9/5. Now to get x alone, we're just going to divide both sides by a negative, and we get this answer, negative natural log base e of 9/5. If I use my calculator, here's what we get. Okay, I hope you can see it. It's a little small here, but I punched in negative. Make sure you use the negative button and not the subtraction button. Natural log and you notice e's not showing there. They don't are going to show it. And I put 9/5 all in parentheses. Let's see what we get for an answer here. We get negative 0.5878. So the answer here is negative 5878. Make sure you're rounding correctly there. Try that with your calculator on your own. Okay? All right. Here's a problem with a log in it, natural log in it. So to undo this, we're going to need to put this into exponential form, and we're just going to translate each of these items, e and 5x and 4, into the places they belong. So let's drag the result down, throw the base e to the other side, and apply the exponent. Now here's a perfect example about why I like to write e here. What if that weren't written there? What if the e were not written there? You might wonder, well, what in the world am I supposed to do? I don't see anything there, and I lose my way a little bit. So writing the e in here on a regular basis will remind you, oh, that's got to go to the other side, and then we apply the exponent. This is the main reason why I want to make sure you write that base in there for a while. All right, then to get x alone, we're going to divide both sides by 5. And here we can use the calculator again. I'm going to use the e to the x key to do this with. So let's take a look at that. All right, I've entered the e to the x key, hit second and the ln button. You notice it's blinking, the cursor's blinking up there, and it's allowing me to put in the exponent. Now to get out from there, I'm going to have to arrow out of there and then divide by 5. Don't really need to put that in parentheses because of the order of operations. And I end up with 10.9196. So x is equal to 10.9196. Okay? All right, as I was setting up for this problem, I reminded myself that I didn't check my answer. If you recall, we always need to check our answers here to make sure that this result, this whole thing here, is not going to be negative, because the result in our problems must be greater than 0, just like the base must be greater than 0 as well. So in this case, we're going to check this one at the end, plus we've got a restriction that may come in because of this inequality. All right, well, I'm going to turn this into exponential form by dragging the result down, throwing the base to the other side, and applying the exponent. By the way, exponents can be negative. It's the result that can't be negative and the base that can't be negative. Now to solve this for x, we're going to add 1 to both sides. X is greater than e to the negative 2 plus 1. Let's take a look at that on the calculator. All right, I'm going to use the e to the x key here again. So second ln, and we're going to put in negative 2. I'm making sure I'm using the negative button there, not the subtraction button. Got to get out from the exponent there, so I arrowed out. Hit the right arrow to arrow out of that. Plus 1, and I end up with x is greater than 1.1353. X is greater than 1.1353. And as I look at that value for x, it's greater than this. It's not negative. If I put it back in here, I will get an answer. Here 1 minus 1 is 0.1353, which is greater than 0. So that works. Now I'm not just checking this number, I'm checking to see what happens when I stick it back in here. And that result is now still greater than 0. So make sure you check your answers. I'm not going to necessarily check them all, but I will be checking the inequalities for you as well. All right, here's a problem from your homework that I thought we'd do here. And I'm doing this one because it's an inequality and we've got some restrictions we got to worry about. So we're going to turn it into exponential notation. So drag down the result, throw the base to the other side, apply the exponent. And when I apply that exponent, I end up with I've written the answer in there. I got 403.42 something there. What it's saying is, what is the exponent on e? If the exponent on e is 6, I should get about 403. Now, we might be tempted to walk away from this problem, but if we put that in here, all the values less than 403 would actually drive you down into the negatives. So those are not allowed. So we're going to amend this answer a little bit and say x has to be greater than 0, but less than 403.4288. Again, it's important that you check that value back in the problem. X cannot be, if I stuck that back in here, x cannot be less than or equal to 0. All right, let's take a look at one more problem here. You notice I've written this is problem 51. I've written this exactly the way it's in the book. There's no e's here. And always looks a little funny to me, so I just go ahead and fill those in. This is e here, this is e to the x, there we go. Now if you recall, we're going to end up using the properties, one of the properties of logs here that says, if I find myself adding two logs, which are exponents, if I'm adding two exponents, the request must have been to multiply. So if I was multiplying here, I would rewrite this as natural log base e of 4x times x. Again, if we find ourselves adding two logs or two exponents, the request must have been to multiply. So let's go ahead and finish solving this. This is the natural log base e of 4x squared equals 9. Now because there's a single log on this side, I can go ahead and drag down the result, throw the base to the other side, and again having that e there reminds me that I can put the base over there, and so I want to get x alone, so we're going to divide both sides by 4. I get x squared equals e to the 9 divided by 4. And now to finally get this problem solved, I would take the square root of both sides. And don't forget, when you take the square root of both sides, square and square root undo each other. And over here I'm going to get plus or minus the square root of e to the 9th all over 4. Now, before we grab the calculator, let's make a note of the fact that if I have a negative here, a negative whatever this is not going to be allowed back up in our original problem, either in here or in here. Doesn't matter if either place is a negative, then that would be an answer that is not usable. So we can't really use the negative answer. So we want the positive one only here. So we're going to grab the calculator and do that. Okay, so you can watch me punch the buttons this time. We're going to take the square root, second square root of e to the x button there, and I want to put in a 9. Now I need to get out from underneath the radical there, or out from that radical, bring it down, and now we're going to divide by 4, arrow out from underneath the radical, e to the 9 divided by 4, and I end up with the answer 45.0086. 45.0086, and I want the positive answer only. And it's important again that we check those answers each time. All right, you'll notice as you do these that the problems are done just the way you did in the past. So if you have some questions about some of these, go back and do them there as well. The base is the only thing that's changed here. Everything is all the same. All right, so that's the end of our video here. You can go ahead and do assignment K, section 10-5 on base E and natural logarithms. Again, all of this is the same as the previous assignment with common logs and those before that. So just apply the same rules and principles. Go back and review anything if you need to. Tomorrow I'll take a look at the story problems in this section. It's an exciting part of dealing with logs because, in fact, exponentials and logarithms are a powerful thing that we will use in many, many calculations we're going to make. So if you have a question, please email me. Let me know if you have a need, if you have a problem you want me to work for you. Go ahead and send that page and problem number, and I'll try to get back to you as soon as I can. Have a good one.